In this video, we're going to talk about related rates. When we talk about related rates, we're talking about rates of change of two or more related variables that are changing in respect to time. And in terms of algebra and calculus, we're going to use the chain rule, and most often we're going to have to differentiate using implicit differentiation. So an example is when water is being drained out of a conical tank, and you're going to have a lot of different variables here. So for example, volume is V, the radius of the cone is R, the height of the cone is represented by H, and then as things are progressing or draining out of this cone, everything is in terms of time, so T. And so the volume equation for a cone, a three-dimensional cone, is this guy right here. So we can actually differentiate using implicit and the chain rule differentiation. So when I'm looking for a rate of change, I'm going to look to take the derivative. So I'm going to look to take the derivative in terms of t. So that'll make it d over dt. And I'm going to need implicit differentiation here because I have multiple variables that are not in terms of t. So if I apply that to the v for volume, it becomes d big V over dt. And then as I take the implicit differentiation of the right side, I'm going to take the pi thirds out because that's just a constant. I'm going to use the product rule here. And remember, with implicit and the chain rule, I'm going to need the d over dt applied to h and to r. So that's why you have dh over dt and dr over dt. So you can do a lot with that, especially when you're plugging in values to solve for one thing or another. But in a nutshell, this is something that I would end up with here. If I'm looking for the rate of change of the volume as water is being drained out of this tank, it's going to be related to the rate of change of the height and the rate of change of the radius of this cone. So in this video, we're going to work through plenty of examples so that we can get a hang of what we're doing. So let's take this first one here. Let's say the variables x and y are both differentiable functions of t, remember t is time, and are related to the equation y equals x squared plus 3. Find dy over dt when x equals 1, given that dx over dt equals 2 when x equals 1. So that last sentence gives us a ton of things to plug in, so likely we're looking for a number as our answer. First thing I do is I take my equation here and I apply d over dt because we're always looking at differentiable functions in terms of t. So let's use implicit to find the derivative of this. So I'm able to differentiate here, and I have dy over dt is equal to 2x times dx over dt plus 0, which doesn't really matter. So I'm able to plug in 1 for x and 2 in for dx over dt, which will solve for dy over dt. So let's do that. So when I plug everything in, I end up with 4, but in terms of understanding what this really says, it says that the rate of change of y in respect to t, so whatever y is in terms of time, when the x variable is 1 and the change in x, or the rate of change of x in terms of time is 2, that means that y is changing at that point at 4, whatever the unit is per whatever the time unit is. So our next example here deals with more specific units, which is actually quite useful. So let's say a pebble is dropped into a calm pond, causing ripples that form in concentric circles, much like is shown here. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. So when the radius is 4 feet, at what rate is the total area A of the disturbed water changing? So this is related rates because we've got multiple variables happening in terms of t or time, and that time is per second. So the first thing you always want to start off with is your base equation. So here we have the area of a circle, so that's going to be a equals pi r squared. We're given a rate, so that's the change in the radius, or dr over dt is 1, so 1 foot per second. We're looking to find dA over dt when the radius is 4. So the first thing we're going to do is take this equation, differentiate it, and plug in what we know. So the first thing I do is apply d over dt to both sides, so that gives me dA over dt is going to be equal to the derivative of the other side, so I'm going to pull out a pi because it's a constant, take the derivative of what's left using the chain rule, so that's going to be 2r times dr over dt, and now I can plug in those variables, or for those variables, so 4 goes in for r and 1 goes in for dr over dt, which leaves me with 8 pi. but I'm not done because I need my units here because I actually have information to fill that out. So because this is dA, or the derivative of the area, and area is in terms of feet squared because it's area, it's two-dimensional, and we're using feet here, and then it's going to be over whatever the denominator is here, which is in terms of t, so whatever our time is, so we're going to use seconds. So the whole answer is 8 pi feet squared per second. So right now is a good time to kind of pause and talk about the guidelines for solving related rate problems. Now we're going to use these in all the examples, but it's kind of nice to have a list if you're that kind of person. So the first step is to always identify all given quantities and the things you need to look for. So that's like word problem 101. And then the second step is to write an equation using the variables that you're going to take the derivative of. And then using the chain rule, implicitly differentiate both sides in respect to time t. So that's why we use d over dt each time. We're going to keep doing that. And then the last step is, after completing the differentiation part, substitute and then solve for all the required rates of change. And here we have some good examples of how to translate words from a word problem, or what we would call a verbal statement, into a mathematical model, which is just using variables and numbers to help substitute or simplify our equations. So for example, if the velocity of a car after traveling for an hour is 50 miles per hour, I would have x is the distance that is being traveled over time, so that's the rate of distance that is changing over time. So dx over dt is going to equal 50 miles per hour when t equals 1. Something else to keep in mind is this example. A gear is revolving at a rate of 25 revolutions per minute. Keep in mind that that is going to be circular. So 2 pi, remember, is circumference. So 1 revolution is 2 pi rad. Remember, we talk in terms of radians first. So theta would be my angle of revolution. And so the change, so d theta over dt, so the change in the angle of revolution over time is 25 times the quantity of 2 pi rad per minute. So whenever you're using something with circles, you're usually going to be working something with like 2 pi rad or whatever it is that they give you. Now let's get back to some examples. So let's say air is being pumped into a spherical balloon at the rate of 4.5 cubic feet per minute. Let's find the rate of change of the radius when the radius is 2 feet. Now my job is to translate all those words into math models or equations that I can work with. So first thing I see here is that the rate of the volume is increasing at 4.5 cubic feet per minute, so that is dv over dt is 9 halves, because 4.5 is the same as 9 halves. I'm looking for the rate of change of the radius, so the change in the radius over time when the radius is 2. And I also need the volume of a sphere, so that's that equation here. Now, I'm going to need to take the derivative of this and apply all these things to it to figure out what dr over dt is at r equals 2. First thing I'm going to do is apply d over dt, and that becomes dv over dt. I'm going to pull out this 4/3 pi. Again, it's just a constant. Take the derivative of what's left, so that r cubed, so I get 3r squared times dr over dt. And here's where I can plug in 2 for r, and 9 halves, or 4.5, whatever you prefer, in for dv over dt. So I'm going to do some algebra and isolate dr over dt, and as a fraction, it's 9 over 32 pi. And if you are looking for a decimal approximate, that is about 0.0895, and then the unit for that is feet per minute, because that is going to be the radius, so that's feet, and then over time, and the time in this case is minutes, so feet per minute. Another thing to note about a problem like this is that the volume here is increasing at a constant rate, but the radius is increasing at a variable rate. So just because two rates are related doesn't necessarily mean that they're proportional. So here particularly, the radius is growing more and more slowly as time increases. Our next example is based around this diagram. So an airplane is flying on a flight path that will take it directly over a radar tracking station, as shown in this lovely figure. So the distance s is decreasing at a rate of 400 miles per hour when s equals 10 miles. So now we're looking for the speed of the plane. So some things that we can turn into equations already is the rate of change. So d of s over d of t is equal to negative 400 because it's decreasing when s equals 10 miles. So we're looking for the speed of the plane, so we can just call that x right here. So dx over dt when s equals 10 and x equals 8. So that comes from just writing the Pythagorean theorem based on these variables here. So s squared is equal to x squared plus 6 squared, which is 36. And if I plug in 10 for s, I can solve for x to be 8. So that's how we got x equals 8 there. So now I have this equation to work with, so I am going to take the derivative of that and see what I can plug in. All right, so I'm going to apply d over dt to this whole thing here. So when I do that, it's in terms of time, which is here in the denominator. So that means that x squared turns into 2x times dx over dt plus 0, because that's a constant, that goes away. And I do the same thing that I did with x squared with s squared. So that becomes 2s times ds over dt. I can plug in negative 400 for that. I've got 10 to plug in for s and 8 to plug in for x. So that leaves me with solving for dx over dt, which I do, and I find it to be negative 500 miles per hour, which represents velocity. Because we're talking about dx, so that's x, that's the distance that we're going away from this radar tracking station. So it's moving at 500 miles an hour, so we can just say that the speed is a positive 500 miles an hour. For our next example, we're going to be working with another triangle, but this time it's about the angle of elevation here of a television camera that's at ground level that is filming the liftoff of a rocket that is rising vertically according to s is equal to 50 t squared. So this is where s is over here. So remember t is time, where s is measured in feet and t is measured in seconds. So the camera is 2,000 feet from the launch pad, and we're being asked to find the rate of change in the angle of elevation of the camera shown in this figure 10 seconds after liftoff. Also notice I didn't include any given rates or things to find, so we're going to actually write these equations ourselves. And something else that I wanted to point out about this image here is that this thing in this little teal bubble is not the representation of the length of this hypotenuse here. It's just this added little thing. It was a little confusing to me at first too, but it's just what tan of theta is equal to. We'll work with that in just a moment. So some preliminary things that I can work with is this equation for s, and that's 50t squared. So I'm going to plug in t equals 10 because that's what it's asking for, 10 seconds after liftoff. So that's 5,000 feet. So wherever there's going to be an s in my final equation, I'm going to plug in 5,000. So I can actually take the derivative, or ds over dt, of this s equation, and I end up with 100t. So that's our rate, which we can also plug in for ds over dt in our final equation. Now, what it's asking for is the rate of change in the angle of elevation, so d of theta over dt, and I have these two other things to plug in there as well. Now you may notice that I am looking for something with a theta in it, but nothing here has a theta in it. But here's where that tan of theta equals s over 2,000 comes into play. Thinking all the way back to basic SOHCAHTOA, the TOA, so tangent, is opposite over adjacent. So I can plug in my s and my 2,000 and have tan of theta equal that ratio, and I can take the derivative of that. So what I'm going to do is take the derivative of both sides in terms of t. So the derivative here using the chain rule, I've got tan of theta, which is secant squared theta times d theta over dt, and so I'm going to separate out 1 over 2,000 here and multiply it by s, so all I have is the constant 1 over 2,000 times ds over dt, and what I can do is I'm going to divide by secant squared theta, which is like multiplying by cosine squared theta. So although I still have a theta in there, we'll get to that in just a moment, what I have now is the replacement of ds over dt, which is 100t, which I have up here. I put that in right there. So I still have some simplifying to do, and I still have some substituting to do. I'll plug in t equals 10, but I have to figure out this cos squared theta. So we definitely need a new slide for this, but I brought over our d theta over dt, and I was able to cancel 100 over 2000 to just give me t over 20. And I'm still multiplying that by cos squared theta, and I brought over t equals 10 seconds and s equals 5,000 feet. We'll plug those in just a moment, but I need to find cos of theta. And I'm going to use this triangle, which I duplicated over here. So using the Pythagorean theorem, I found the hypotenuse to be the square root of the square of s and the square of 2000 added together. And using our handy dandy SOHCAHTOA, adjacent over hypotenuse is going to give me cosine of theta is equal to 2000 over the hypotenuse here. So I'm going to plug that in for cosine theta and square it, because that's the same thing. And so I end up plugging this all into my calculator, and I get this really long decimal here, and using math, frac, it's actually a fraction. It's beautiful. So that means that at 10 seconds after takeoff, the angle of elevation is changing at a rate of 2 over 29 radians per second. And here we have our very last example, I promise. So in the engine shown here in this figure, a 7-inch connecting rod is fastened to the crank of a radius which is 3 inches. So this little triangle here matches to this guy right there. So the crankshaft rotates counterclockwise at a constant rate of 200 revolutions per minute. So let's find the velocity of the piston when theta here is pi over 3. So I'm going to first start with d theta over dt, because it tells me that this thing is moving at a constant rate of 200 revolutions per minute. So that's 200 times the distance it goes around in a revolution. So that's 2 pi. That's the circumference of a circle. So d theta over dt is going to be 400 pi radians per minute. And I'm looking for dx over dt because I'm looking for the velocity of the piston. So that's going to be x here, the change in that, when theta is equal to pi over 3. Now my next step is to find an equation that works with both theta and x in terms of this non-right triangle here. And that's where law of cosines comes into play. So I can actually write an equation with theta and x in it so that I can take the derivative and plug in all the stuff that I have. So I'm going to use this equation here to model this guy using 3, 7, and x as my sides. And once I simplify it down, I'm going to have 40 equals x squared minus 6x times cos theta. So let's take the derivative of this, see what happens. First things first, I wanted to walk you through how I approach the derivative process here. So I can take the derivative of 40, that's 0, and x squared is 2x times dx over dt. And then this bit here, I'm going to pull out a 6, and I'm going to need the product rule here. So that's x times negative sine theta times d theta over dt plus cos theta times 1 over times dx over dt. So I distribute the negative 6 out in this line, and I notice, all right, I have dx over dt here. I'm going to isolate that and have 2x minus 6 cos theta here. And I'm going to subtract this term here to move it over there. So that will allow me to isolate dx over dt as this on our numerator and this thing here as our denominator. So now I'm going to plug in what I have. So what I have is d theta over dt, and I'm going to replace that with 400 pi right here. And I'm going to replace every theta, so sine theta and cos theta, with pi over 3. Sine of pi over 3 is rad 3 over 2, and cosine of pi over 3 is 1/2. And so when I simplify it just a little bit, here's what I'm left with, but I still have this x in here. I'm wondering if we can solve for x. Do you remember this equation? So it's got an x in it, it's got another x in it, and I actually know what theta is in this example. It's pi over 3, so I wonder if we could plug some things in and solve for x. Now I plugged in pi over 3 here, which gave me 1/2, and so I've got a quadratic on my hands. I put it all together, I factor it out, and I have x equals 8 and x equals negative 5, and because x is a side length of a triangle, a 2D shape, it can't be negative. So I'm going to plug in 8 for x and solve for dx over dt once and for all. I plug in 8 for both instances of x, I plug that whole thing into my calculator, and I get this really long negative decimal. I'm going to approximate dx over dt, so that's the velocity of the piston at theta equals pi over 3, so it's going to be about negative 4,018.2632 inches per minute. And just to note that our velocity here is negative because x represents a distance that is decreasing. All right, that's going to do it for this video. Thank you for watching.